Nikunj?
Sorry, rookie mistake. I was muted. Hi, thanks, Mike, for inviting me for this talk, and thank you everyone for taking our time to attend this. And as Mike said, I would be talking about a mathematical exploration of language models. So, okay, so language models, in the simplest words, are just next word predictors. So for any given context, that is a piece of text S, your language model will try to predict what is the next word that could follow this piece of text. For example, if you're given a context S, that is, I went to a cafe and ordered a language model will try to predict what is the next word that could follow this context S. And it does so by outputting a distribution over words. And for example, it could assign high probability to words like latte or a bagel that could potentially follow such a context, but low probability to words like dolphin, which hopefully are not very likely to follow this context. And such language models are typically trained just using access to a very large unlabeled corpus. For example, you can think of all of Wikipedia as a good example for such unlabeled data. And this unlabeled data is used to construct these pairs of S and W. So S being a context, so you can just take any sentence or any partial sentence from this corpus, and W then can be the word that follows this context. And you can get these pairs S and W. And you can train the language model to minimize the following objective, that is a cross-entropy objective, which again, in simple words, all it tries to do is for the S and W pairs that are observed in this unlabeled corpus, it tries to assign high probability for that particular word. So it tries to assign high values to PS of W for the Ws that did follow the contexts S in the unlabeled corpus. And this setup looks quite simple enough. All you need is unlabeled data and some neural network that parameterizes this language model and minimizes objective. And it turns out that this very simple setup is actually turns out to be quite useful to solve certain downstream tasks. For example, it turned out to be useful to solve the task of text classification. So for text classification, it's like a classification task on top of sentences. So examples could be classifying movie reviews as either a positive or a negative movie review in terms of the sentiment towards the movie, or classifying a sentence into one of many topics that the sentence might be talking about or an article might be talking about. So yeah, so using a particular recurrent neural network architecture, which has some 24 million parameters, you could use a language model that's just trained using the cross-entropy objective and fine-tune it to solve text classification. Subsequently, with progress made in scaling up deep learning and in architecture design, it turned out that the same objective, the same setup, but with a much larger language model and a much larger text corpus, could not now solve not just text classification, but many other downstream tasks, like text generation, where you're given a prompt, let's say it was a bright sunny day and you want to predict or you want to generate coherent text that could follow this prompt. And you could do this by just predicting one word after the other using the language model. Or the task of factual question answering, where you want to answer a question like, what is the capital of Spain? It also helps with the task of machine translation, where you want to translate an English sentence to its French equivalent, let's say. And of course, it helps with sentence classification. And in fact, soon after, it turned out that with an even larger language model, with an even larger corpus and even larger set of authors, you could train a language model that not only does well on these tasks, but can actually solve them using very little label data for these tasks. And in some cases, you could also solve these tasks in the zero shot setting, where you don't even have labeled data and all you know is what this task is about. It's translating from English to French, let's say. And this is quite interesting because all you needed to do was train on the simple cross-entropy objective, and you can already see benefits on many downstream tasks. And in this talk, the main question that I would be focusing on is why is it the case that solving this task of next word prediction can help with seemingly unrelated downstream tasks like question answering or sentence classification? And also, why can it help solve these tasks with very little label data? So I'm just going to divide this talk into two parts. In the first part, I'll talk about the general framework of solving a task A, and that helping with another task B. And in this case, language model does fit into this framework because task A is next word prediction and task B is some downstream natural language processing task. And in the second part, I'll talk about our recent results for language models that all in this framework. And this is joint work with Sadiq Amaladi and Sanjeev Arora from Princeton University. Okay, so I'll dive into why does solving task A help with task B. And as I said earlier, language modeling fits into this framework. And to understand why this helps, we actually observe that humans do this all the time. So humans can summarize the knowledge and experience gained from solving a task A and the skills learned in the process of solving task A to solve a new task B quite efficiently. For example, task A could be riding a bicycle and task B could be riding a motorcycle. You see that you could already learn skills like balancing and making a turns while riding a bicycle, and that can help with riding a motorcycle. Another example is the skills that you learn while trying to get a math degree can potentially help you do well in law school. There are a lot of skills that you can learn. You can learn how to learn efficiently. You could learn tricks for how to ace tests, for example. And perhaps a more classical example is that from the movie The Karate Kid. I'm sorry, I'm going to give some small spoilers, but hopefully not a lot. So in this movie, the protagonist wishes to learn karate, and he goes to his instructor. However, the instructor or his teacher, instead of teaching him karate on day one, asks him to do some really basic chores like painting the fence or scrubbing the floor or waxing a car. And this did frustrate the protagonist because he wanted to learn karate. But it turned out that some basic movements involved in doing this basic chores actually helped him learn some karate moves quite easily, and he could excel at karate. So yeah, so as with a lot of machine learning paradigms, motivated by the fact that humans can do this, that learn from task A and solve task B, this has been adapted in machine learning. So the typical pipeline for this is as follows. In the first stage, you pre-train a model on task A. So let's say you parameterize a model using neural network architecture. Then you can learn the weights of this neural network by solving a task A. And the second stage, you can use this learned model on task B in one of many ways. So a very standard approach is to, let's say, use the weights that were learned for this model as initialization for a new model. And this new model is then going to be fine-tuned on the task B using some amount of label data that's available for this task. Another standard approach is to extract some features from this learned model and learn a classifier on top of these fixed features for task B. So these features could be, for example, the output of some layer of the neural network for any given input. So rather than using the input for the task B, you use the representation that is outputted by the neural network at some layer, and you learn a classifier on top of it. And in a lot of cases, you can use some special properties about the architecture that is used to parameterize this model and find some innovative ways to use this. However, the main benefit that this offers is that doing this can be much more data efficient as compared to supervised learning. So solving the task A first can help, eventually only requires fewer label data for solving the task B than would be required if you're solving task B from scratch without having task A. And different choices of task A and task B kind of lead to different machine learning paradigms. I'll just give a very broad summary of a few of them. So one is that of transfer learning, in which case the task A could be a very large supervised learning problem. For example, you could use the dataset, ImageNet dataset, that has more than 1,000 classes for images and more than 1 million examples. And you can learn a model on this task and then subsequently use it for other image related tasks, like, for example, detecting diseases from X-ray images. Another paradigm is that of meta learning, where task A is essentially you have access to many small tasks, but all of these tasks are going to be related to the eventual task B that you're interested in. For example, you could solve the problem of handwritten character recognition. And in the first stage, you can solve this for many different languages. And your new task is somehow related to this. So it could be handwritten character recognition again for a new language that you did not encounter in the first phase. The paradigm that we are going to be interested in, however, is that of self-supervised learning. And language modeling also fits into this. And this is where task A is constructed using unlabeled data, and task B is any downstream task of interest. And this paradigm has actually been quite successful, and it's gaining a lot of popularity recently. And in fact, a lot of prominent researchers are also uh, quite interested in this problem. So Jan LeCun, who's the director of Facebook AI research and also a Turing Award recipient, has been quoted saying that this is the single most important problem to solve in AI. And the problem being self-supervised learning, that is using unlabeled data uh, to learn skills, for example. I know that the big difference between the first kind of tasks and the second one is uh, in the first case, you require labeled data in the task A, at least you need some supervised learning problem, but here you only need unlabeled data in the first phase, and that already helps you with downstream tasks. So I'll quickly describe what self-supervised learning is. So self-supervised learning is motivated by the following observations. The first being that humans can in fact learn a lot about the world by just observing it or interacting with the world. And we don't necessarily need explicit supervision all the time. Secondly, while deep learning has been successful at solving supervised learning quite well, when a lot of labeled data is available, the classical example is that of ImageNet, image classification, sorry. Labeled data can be quite expensive to obtain because it often requires human annotators, and in some cases, even expert annotations. So it could be expensive and time consuming. Unlabeled data, on the other hand, is available in abundance and is quite cheap to obtain. So you have a lot of text and a lot of images available freely on the internet. And the principle that guides self-supervised learning is that you want to use this unlabeled data that's available to generate labels and construct supervised learning tasks from this unlabeled data, and then learn to solve them. And this simple principle has led to many practical algorithms that have been quite successful recently. And in fact, they do well on many standard benchmarks and sometimes even beat vanilla supervised learning, where you just used all the label data to learn a model from scratch. And I'll just give some examples of self-supervised learning methods. So in images, what you could do is you could try to predict the color of an image from the black and white version of it. So you can just take an image and you can separate out the color and the black and white version of it, and use the black and white version and try to learn a model that learns the color that was present in that image from the black and white version. Other tasks include reconstructing small parts of the image given the rest of the image. So now your input is the entire image except for a small portion, and your target that you're trying to predict is the portion that you took out. Or you could try to predict the rotation. You can apply a random rotation to an image and try to predict what rotation was applied to it. And for all of these tasks, you just need raw images, and you're constructing these tasks from these raw images. You can do the same thing in text. So some popular methods that work in practice are you can try to learn a representation function that can make consecutive sentences in a text corpus, or even two halves of the same sentence that are available from the text corpus, to have representations that are close to each other in some metric. And of course, the task of next word prediction also fits into this, because you're using text and breaking them down into a context and the next word and trying to solve next word prediction. Or you could try to fill in multiple blanks in a sentence. So you see, there's a diverse set of tasks that can be constructed from unlabeled data, but the one thing that they have in common is they all help with solving downstream tasks. And this intriguing success of self-supervised learning is not really well understood. And in fact, we have very little mathematical understanding for why self-supervised learning helps. And as we have seen, this seems to be an important problem. So it could help with some mathematical understanding, could help, because theory can potentially help with trying to formalize the notion of what are skills learned from tasks. Or you can also ground some existing intuitions about why these methods help into math. And then hopefully trying to manipulate the math here and there, you can maybe get new insights that can help improve and design practical algorithms, better practical algorithms. And there is a rich literature for the theoretical understanding of supervised learning in the form of statistical learning theory, and also related problems like transfer learning, domain adaptation, etc. However, they don't exactly capture this setting, and the main issues being task A and task B here are quite different from each other. Like next word prediction is not directly related to that of, let's say, machine translation or sentence classification. And also task A, the first pre-training that you do is in some sense agnostic to task B. So you don't have labels for task B. You don't even know what tasks you might be interested in, but you're just going to solve task A without knowing task B. And in the rest of the talk, I'll describe our attempts at trying to understand one such method, which is language modeling. So this is just a brief overview of the entire setup of training on task A and that helping with task B. So I'll just pause you for some time to see if there are any questions about the setting.
In the examples that you gave in the introduction, task A and B were not entirely unrelated to each other, right? So we shouldn't expect that something that can perform very well will be able to perform any other arbitrary task well, right?
Right. So yeah, okay. I'll clarify what I meant by different here. So for example, you're right that in some sense they are all tasks about that. For example, in language modeling, helping with sentence classification, they are all tasks about trying to understand language better. However, if we wanted to mathematically understand why this works, for example, in the case of supervised learning, how this is done is you assume that the data that you have, the label data that you have, and the data that you're going to test on are IID samples from some underlying distribution. So this is a kind of assumption that that you have on your data to show such guarantees. Even in the setting of domain adaptation, the typical assumption to make is that task A and task B are essentially the same, that you're still doing maybe image classification, but maybe the distribution of the images are changing and the distribution of labels given an image are changing slightly. So in that sense, task A is just next word prediction and task B is sentence classification. And why are these mathematically connected? And this connection is not a priori clear. And yeah, I meant different in that sense.
Well, it seems like what you're doing is exposing some kind of, I guess, correlations between the data sets in each task that are just not as obvious as there would be in two different image sets. Is that correct?
Right. That's a good intuition to have. Yes. So we do want to say what's the connection between this task A and task B. There is some connection that is helping you. So we're trying to understand what is this connection. There could be multiple factors that affect this, and I'll get to this later.
Thank you.
Yeah. Okay. So yeah. So that's the first part. And now I'll move on to our work on a mathematical exploration for language models. So just as a recap, a language model was basically the task of next word prediction. So for a context S, a language model will output a distribution over words, P sub S. And as with any task A, task B setting, we're going to do it in two stages. So in the first stage, you pre-train a language model on the task of next word prediction using the cross-entropy objective, using data from, let's say, a large unlabeled corpus. And in the second stage, you use a language model for a downstream task. And the question that we were interested in is why should next word prediction help solve perhaps not unrelated, but a different downstream task with very little label data. And there are a lot of factors that could affect why next word prediction helps a downstream task. So there are different aspects of pre-training that could help. So in this work, we focus on the setting, we focus on the role of the particular task of next word prediction and the objective function. And we try to understand why does next word prediction intrinsically help? And what is cross-entropy objective a good measure for evaluating next word prediction. There are other factors like the model architecture that is used or the training algorithm that is used in order to do pre-training. For example, it's possible that the particular architecture, like the transformer architecture, in that attempt to solve next word prediction, somehow due to some inductive biases, naturally learns good and useful representations for many kinds of NLP tasks. And this is indeed the case in images, let's say, because convolutional neural networks, even though trained on one task, some image classification task, end up learning some very general purpose features or filters in the convolutional layers that are like clearly useful for other image related tasks. However, understanding this inductive biases of model architectures and training algorithms like gradient descent is actually it's a hard problem in theory of deep learning, even for not very deep neural networks. So we keep that aside for now, and we focus on, is it the case that next word prediction intrinsically helps with language modeling or not? Secondly, we focus our attention only on the downstream task of sentence classification. Of course, this is just one of the many NLP tasks that one would be interested in. However, as a first cut analysis, we find that looking at sentence classification already gives us interesting insights. And hopefully, at least some of these insights can be used to understand other downstream tasks, NLP tasks like question answering, etc. And the next thing we restrict ourselves to is how do we use a pre-trained model for a downstream task? And here we take a representation learning perspective. So what we do is we use the language model that is trained on next word prediction to extract some features from it. So to extract representations, that is a mapping from sentences to vectors. And then for a downstream task, we're going to fix those representations and learn a linear classifier on top of it using the label data that's available. And linear classifiers have a lot of benefits, like you can understand the data efficiency or sample efficiency of linear classifiers because it depends on the dimensionality of the representations, etc. And it also is quite effective in practice. But the best reason for using linear classifiers is that it's easier to do math with. Note that fine-tuning these representations and not just fixing them for a downstream task does indeed boost the performance in practice. However, again, just like inductive biases, understanding fine-tuning and quantifying the benefits is not a very easy problem, especially given our current tools that we have for deep learning. So yeah, so to summarize the theoretical setting, we have a language model. We are going to use it to extract a function feature map f that maps, let's say, sentences to d-dimensional vectors. And given a downstream classification task, sentence classification task. So suppose you're given the task of classifying movie reviews into positive or negative sentiment. You can use this feature map to embed all the movie reviews into vectors, into a vector space. And then you use label data that you have for this task to learn a linear classifier that separates these vectors from different classes. And the precise question that we want to answer is, why can language models that do well on next word prediction, as measured by the cross-entropy objective, learn features that are useful for solving classification tasks with linear classifiers? So this is like the one-line summary of the setting that we're interested in. And with this question in mind, we can show the following. So we first have the key observation that we can actually phrase a lot of classification tasks as some kind of sentence completion problems. And once we do this, we can actually see why the task of next word prediction is meaningful, because you can use that to complete sentences. And we then formalize this intuition of sentence completion into a mathematical statement, and we can use that to show some guarantees for language models. So we can show that language models that are epsilon optimal in the cross-entropy objective, that is one language models that do well on next word prediction, epsilon close to as well as they could, they can learn features that can linearly solve such classification tasks up to some error of square root epsilon. And we also experimentally verify some of the assumptions and some of the theoretical insights that we get out of this analysis. And we can also use it actually to design a new objective function that does reasonably well in practice. Okay, so for the rest of the talk, I'm first going to describe what like an abstraction for language modeling that's useful for the rest of the talk, and then describe how downstream tasks can be rephrased as sentence completion problems, and then show the formal guarantees, and then have some discussions about what these guarantees imply and what more can we do with it. Okay, so I start off by discussing language modeling in more detail. So again, as earlier, you have a context S, and language model predicts a distribution over words. So you can just think of this distribution outputted by a language model P sub S as a vector of V dimensions, where V is the size of the vocabulary. So typically V would be of the order of, let's say, 50,000 or 100,000. That's the total number of words or tokens that you have. And the goal of language modeling is try to make this distribution PS close to the true distribution over words that could follow this context. So we call this true distribution P star of S. And note that the word that could follow context S is not actually a deterministic function, because there could be multiple words that could follow any given context. And this is characterized, this uncertainty is characterized through this distribution P star of S. So this will assign high probability to words that might follow a given context. And now we get samples from this true distribution P star using this unlabeled corpus, where we just see one word that follows a given context. And we use it to minimize the cross-entropy objective as earlier. And now the first question we want to ask is, what is the best that a language model can hope to learn? That is, what is the minimizer of the cross-entropy objective? If I can do absolutely well on this objective, what can I learn? And a well-known result about the cross-entropy objective is that the minimizer of it is basically the true distribution P star itself. So if you manage to absolutely minimize the cross-entropy objective, you are learning the true distributions. Exactly. So, and the proof of this is also not, I mean, it's pretty much straightforward. So it's just rewriting the cross-entropy objective as a KL divergence between the true distribution and the predicted distribution. And once that is done, you can see that the KL divergence is minimized when the distributions are the same, and hence you can recover the true distribution P star. So at least now we know that language models are aiming to learn this true distribution P star, and cross-entropy objective at least can help it do so. However, in practice, language models are never unconstrained. So a very typical setup for language modeling is the following, where you first take a context S, you pass it through some neural network architecture, let's say a transformer architecture, and you embed it into D-dimensional features, where D is typically of the order of, let's say, 1,000. So it's much smaller than the size of the vocabulary. And these features are then hit with a word embedding matrix. So this matrix is of size D times V. So each column of this matrix corresponds to a word, and the vector at that column corresponds to the word embedding for that word. So it's a D-dimensional word embedding for all the words. So yeah, you can multiply these two and you get these logits, as you do typically in classification as well. So you get this V-dimensional logits, and then you take a softmax over this to get a distribution P sub F, a P of F of S. So I call this distribution the softmax distribution that depends on the feature map F, that is how it maps sentences or context to vectors, and the word embedding matrix phi. And as before, the goal is to minimize the cross-entropy objective, but now you use the softmax distribution instead. And now we ask this question. So is it the case that we can still learn the true distribution P stars exactly, especially in the case where D is much smaller than V? And note that we have much lesser degree of freedom than we had earlier, because we only have D degrees of freedom here. And it turns out that you can't actually always guarantee to learn the true distribution P star exactly. But what you can show is that for a fixed word embedding matrix, the feature map that optimizes this cross-entropy objective will learn a distribution P F star of S that is not exactly equal to P star, but it is equal to P star on the when hit with the matrix phi, the matrix of word embeddings. So the left and right side of these equations are D-dimensional vectors now. And this tells us that while you can't guarantee PFS to be exactly equal to P star S, you can guarantee them to be equal on a subspace. And this subspace is the D-dimensional subspace that is spanned by the rows of the word embedding matrix phi. So this tells you that the cross-entropy objective somehow lets you learn this true distribution P star in a linear fashion. You learn some linear projection of the true distribution. And in fact, the proof of this is also not that complicated, but all you need to do is use the first order condition for the softmax objective. Like you set the gradient to 0. Yeah, it's also a convex objective in the features fs, not in the weights of the neural network, of course. So yeah, you can just set the gradient to 0 and you get that you learn this true distribution on the subspace. So note that so here, first of all, note that we are looking at the absolute minimizer of the cross-entropy objective, which you might not achieve because you never actually get to true optimality for various reasons. You can't optimize perfectly. You don't have enough samples. And another important reason could be that the neural network that you use to parameterize these features are not expressive enough. But here we're ignoring all those factors, and especially the expressivity. We're assuming that we're treating the neural network as a black box. And if you could learn arbitrary features, you can still learn the true distribution on a subspace. Thus, a quick summary of this is that language models with cross-entropy aim to learn the true distribution P star. But if you use softmax language models with some word embedding matrix D, you are only guaranteed to learn it on a D-dimensional subspace rather than the entire distribution. So I'll just pause it to see if there are any questions about this.
Hey, is the matrix phi also learned from data?
Right. So yeah, that's a good question. I forgot to mention that. So in practice, the word embedding matrix phi is also something that is learned.
Yeah.
However, we do not actually have a good closed form solution for what the optimal word embedding matrix would be. But what you can't do is, let's say you learn some word embedding matrix and some feature map F. You can, at the end, fix the word embedding matrix and just train the feature map that at least minimizes the cross-entropy objective for that word embedding matrix.
Okay.
And as we'll see later, if the word embedding matrix satisfies some nice properties, then pretty much any word embedding matrix that satisfies those properties will help us show guarantees. You need not even learn them if you have some pre-trained embeddings that satisfies those properties. So let's say some standard word embeddings like glove or word2vec. You could potentially just use them and just train a feature map. And that's also sufficient to show guarantees.
Got it. Thanks.
Yeah, that's a good question. Thank you. Okay, so if there are no more questions, I'll move on to the next part, where we're going to see how classification tasks can be rephrased as sentence completion problems. Okay, so suppose you're given this binary classification task of sentiment analysis. That is, you're given movie reviews and you want to classify them as either positive or negative sentiment. So we saw that language models aim to learn P star of S for NES, or at least P star on a subspace. And in order to be able to show guarantees for language modeling helping with such tasks, we at least need to show answer a basic question. That is, if we had access to this P star of S, these true distributions of words that can follow a given context, can we somehow use it to solve the task? So we perform this thought experiment. So suppose I give you a movie review, which is, I would recommend this movie, and I give you the true distribution of words that could follow this movie review. Can you use it to get the sentiment for this movie review? And I'm sure that if you think about this for a bit, you would come up with some interesting strategies. But a very simple strategy is the following. So what you can do is use this entire vector of probabilities that you have and just look at two values from this. That is the probability that is assigned to the smile emoticon and the sad emoticon. And note that a positive movie review is more likely to be followed by a smile emoticon. So perhaps comparing the probabilities of these two might give a good indication of what the sentiment for this movie review is. And this simple strategy can also be rephrased as follows: as learning as a linear classifier on top of this vector of probabilities, where you have +1 for the entry of smile emoticon, -1 for the sad emoticon, and zeros everywhere else. And now this strategy is essentially trying to learn is basically a linear classifier. So it's saying V transpose P star of S is greater than 0 or not. So that's nice. So we see that at least in a very simple way, you can convert classification task into sentence completion problems. But can we do better? Because this vector P star has a lot of words. It has like 50 to 100,000 words in it, and we're just using 2 out of it. So you can do the following too. You can do the following. So what you can do is add a prompt, "This movie was," at the end of every movie review, and treat this combined sentence, which is "I would recommend this movie was," as the new context S. And now use the probability distribution P star for that particular S. And now you see that you can use a much larger set of words like good, brilliant, boring, interesting. And this can potentially help you get a better sense of what the sentiment of this movie review is. And perhaps you can now take some weighted combination of the probabilities for all of these words, and again express the prediction strategy as a linear classifier on top of this vector of probability P star. And this strategy of adding prompt helps us in multiple ways. So it can allow, first of all, a larger set of words that are grammatically correct completions. So you can make use of this vector of probabilities much more efficiently. And you can also extend this to other kind of classification tasks. For example, we'll see later that a task that tries to identify the topic of a news article can also be solved in this way by adding the prompt, "This article is about," at the end of every news article, and then you can try to predict probabilities of certain words that are related to different topics. Okay, so now that we at least intuitively see that we can rephrase data sentence completion problems, we try to test this in practice. So we take the standard sentiment analysis dataset, and we try to see if you can solve it using linear function of P star. But of course, you don't have access to P star. So instead, as a proxy, we use the output probabilities from a pre-trained language model. In this case, it's the GPT-2 language model. And we use those probabilities as a proxy for P star. And we try to see if we can solve these classification tasks as a linear classifier on subset of words from this probability vector. Okay, so we observe the following. So for this task, which has two classes, if we just look at the probability of these two tokens, the smile and the sad emoticon, and just learn a linear classifier on top of these two-dimensional features, we see that we already get up to 76% accuracy, which is much better than random guessing. Random guessing in this case is pretty much 50%. And in fact, if we use a larger set of words, so if we use 20 words in total, and these words we just pick, like, don't really cherry pick, you just pick all the words that make sense, basically, like good, great, boring, etc. Just learning a linear classifier on top of these 20-dimensional features already gets us up to 78. And importantly, we note that if we, instead of just using the like raw movie reviews as inputs, if we add a prompt, "This movie is," at the end of all sentiments, at the end of all the reviews, we observe a big boost in performance. So in some sense, this also validates the fact that you can try to use a language model better if you actually add this prompt, which is making the completions more grammatically correct. And this is also an observation that this has also been observed in like multiple other empirical papers more recently. So you see that you can already get up to like 83% on this task. So just to give a sense of what a good performance is on this. So a very standard baseline is to use the output features themselves, the d-dimensional features, in this case that's 768, and learn a linear classifier on top of it. And that gets around 87.6. And in fact, if you add a prompt, you can already get up to 90. And actually, I don't have the number here, but fine-tuning these representations further on the downstream task can boost the performance by 2 or 3% more. But essentially, these numbers are pretty good. And note that we used the output probabilities from a language model as for these numbers, and not the true P star, of course. And one could argue that maybe it's some inductive bias of these models that helping maybe get good performance, and not the fact that they're doing well on the next word prediction task. So for that, we just look at the randomly initialized transformer architecture, basically the architecture that is used for this, and that does pretty poorly. That is basically the same as random guessing. And another standard baseline, a very classical baseline for NLP, gets around 80%. So you see that basically just using the output probabilities from a pre-trained language model and taking a subset of like some 20 words and adding a prompt to a movie review gets you to pretty good performance, like beating even a very simple baseline like bag of words. So yeah, so to summarize, hopefully this kind of convinces you that you can rephrase classification tasks as sentence completion problems, and also that you can rephrase this. You can treat this rephrasing of sentence completion problems as solving the task with a linear classifier on top of the vector p star of probabilities. So I'll just pause it to see if there are any questions, because next I'm just going to quickly do a run through of what are the results that you can show with this formalization.
Did you look at predicting two words? So you have a first word and then that's an S prime and a second word.
Right. Yes, that's a good question. And you can actually do this. For example, you could have predicted this movie is not good. This is something that we are thinking about. So there are a few issues with this, but I guess one simple issue is that as you predict more and more words, since you're using the language model to predict one word of the other, the error that a language model has gets compounded. So it gets added up as you predict more and more words. And in the worst case can actually be linear in the length of the sequence that you're predicting.
Yeah.
So yeah, this is definitely something that can be done. We did not explore this a lot in our experiments, but yeah, it's an interesting thing to try as well. And in fact, this can also be useful for other tasks like question answering, where a language model is used in this way, where you don't just predict one word, but you might want to predict a sentence as an answer, and then you can keep generating the answer. So yeah, this is definitely an interesting paradigm too. Okay, so now I'll quickly go over what kind of results you can show using this kind of formalization. Okay, so since I said that sentence completion reformulation is essentially like being able to solve a task using a linear classifier on top of P star. So we define this, we use a standard metric for doing well on linear classification, that is the logistic regression loss. So for any feature map G that maps sentences to vectors, you can evaluate this feature map by first using it to embed all the sentences into vectors, and then learning a linear classifier on top of it, this V, and then measuring the standard logistic regression loss for that linear classifier. And now we formalize the sentence completion intuition into this notion of natural tasks T. So we say a task T is tau natural if the logistic regression loss for this task, when using P star, the two probabilities as features, and learning the best linear classifier on top of it, is upper bounded by tau. So in really simple words, tau captures how amenable this task is to the sentence completion reformulation, and what is the smallest loss you can achieve by learning a linear classifier on top of these vector of probabilities if you use those as features. So it's just a mathematical formulation of this sentence completion intuition. And now I'll describe the main results. And remember that the kind of result we wanted to show was, why can language models that do well on the cross-entropy objective learn features that can solve classification tasks of interest with linear classifiers? So with that in mind, suppose you have a language model that is epsilon optimal in cross-entropy objective. That is, it does well on the task of next door prediction, but it's not optimal because you can't hope for optimality. So it's epsilon close to the best cross-entropy objective that you could have achieved in language modeling. And suppose you have a tau natural task, and that just means that this task can be reformulated as sentence completion problem. And you have a word embedding matrix that is in some sense nice. And one nice property, for example, for word embeddings to have is that it assigns similar embeddings to words, to synonyms. So good, the word good and nice, let's say, should have embeddings that are close to each other. And if it has some such nice properties, you can show the following guarantee. Where on the left-hand side, you have the logistic regression loss on the task. If you use these d-dimensional features, phi times p of f. So note that p of f was a v-dimensional vector, and when you hit it with the word embedding matrix, you convert it into a d-dimensional vector. So it's a linear projection onto the subspace of phi. So if you use these d-dimensional vectors and measure the logistic regression loss, that is upper bounded by a sum of two terms. The first term is tau, which is just measuring how natural the task is. And the second term is the loss that you would suffer due to the suboptimality of the language model. So epsilon here is the difference in the cross entropy of the language model that you have learned and the best language model that could exist, which is the true distribution P star itself. And actually, like in the paper, we have you can actually show a stronger result where you don't actually compare the suboptimality with respect to the true distribution, but you just need to compare the suboptimality with respect to the best d-dimensional feature map. So you just compare it to the best Softmax language model that uses the same set of word embeddings, and you just suffer that suboptimality here. So yeah, this is a guarantee that we can show. And to see why this kind of answers the question that we were hoping to answer, we are showing guarantees for a language model that's epsilon optimal and cross entropy. So it's doing well on the cross entropy and objective and on the next word prediction task. We're showing that you can use this language model to extract d-dimensional features out of it, which in this case is taking the output probabilities and hitting it with the word embedding matrix phi. And we're showing that it can do well on classification tasks that are natural. And you can solve it using linear classification because you're showing an upper bound on the logistic regression loss for that task. So in some sense, this result kind of answers the original question that we set out to answer. So we'll just take a quick look at these d-dimensional features. So we call these the conditional mean features, the phi times p f of s. And essentially, you can think of it as taking a weighted combination of the word embeddings, weighted average of the word embeddings, where the weights for any sentence are determined by the probability that the language model assigns to the particular word for that sentence. And this is an object that like we haven't seen before. This is not something that we have seen before being used in practice. And it came out of theory. It came out of analysis. So we wanted to see if this actually does well in practice. So this is the earlier table that we had where we actually picked out 20 words from the probability vector and also looked at the feature map directly. So these conditional mean features are also d-dimensional, so 768 dimensional. And actually you see that it gives a boost over the performance of just using this like 20 set of words that we just picked manually. And again, notice a boost in performance when you add this prompt. So you get up to 87%, and now you're like closing in the gap between the standard approach of like using the features from the language model directly. And in fact, you can do this for another task, which is the news article classification task, as I said earlier, which has 4 classes, that is classifying news article into either science, politics, business, or sports. And you can do the same strategy. So you see that the conditional mean features does pretty well on this 4-way classification task, pretty close to the baseline of using the representations from the language model themselves. And again, adding a prompt almost in all cases actually boosts the performance by quite a bit. And we also so what we did is we just checked whether this kind of square root epsilon dependency holds in practice. So we just look at different checkpoints at the training of a language model, and you'll measure the logistic regression loss. So the y-axis is that, and the x-axis is the cross-entropy loss of the language model. And you see that there is some kind of square root epsilon relationship. I'm not sure we can read much into it because these are generally upper bounds and they're quite vacuous, just like any other upper bound, even in supervised learning. But it was interesting to see that there's some kind of square root epsilon pattern that is observed.
Just so I understand your weighted average, the PFS here is the softmax probability for the context S and then the next word W. So it is also determined in terms of the phi W's and BF.
Correct.
Yeah, okay.
That's right. The probabilities here are also determined by the word embeddings. That's right.
Okay.
Yeah. And here S could either be the raw sentence itself, or it could be the sentence with a prompt appended to it. So yeah.
It seems like a very natural prescription. So
it's interesting. And I mean, a priori, we didn't actually expect this to do, at least it was surprising to us that it did as well as it did, because yeah. I mean, even though it's not perfect and it has like, yeah, we'll get to that. But yeah, any more questions about the experimental verification results? Okay, so what are the main takeaways from this? So the first one is you can rephrase classification tasks, or at least some of them, as sentence completion problems. And that can be formulated as being able to solve them as a linear function or linear classifier on top of these vector of probability P star. And once we formalize this the right way, you can show simple guarantees that language model that is epsilon optimal will be square root epsilon well, will do square root epsilon well on these tasks. And in some sense, this like formalizes the intuition that the stronger the language model you have, the larger language models that you build typically will do better on this cross-entropy objective. And at least as an upper bound, you see that, okay, that makes sense. You want to do as well as you can on the language modeling objective. Yeah, the other interesting thing is that we saw earlier that softmax language models, at least without any more assumptions, can only hope to learn the true distribution on a subspace, on a d-dimensional subspace. And this subspace is determined by the word embedding matrix that you have. That is either learned, or you could also use some fixed word embedding matrix that you have. And it's good to understand what are properties that you want these word embedding matrix to satisfy. And one such property that we, at least we have some discussion about it in the paper, is that it's good to assign similar embeddings to synonyms. And yeah, as I discussed earlier, conditional mean features is something that comes out of the analysis. And yeah, it's at least a mathematically motivated way to use to get d-dimensional features from a language model. So yeah, so we have more results in the paper. So the first thing is that you might have noticed that there is always a gap between using the features fs directly as compared to using the conditional mean features. And in the paper, we have some results that kind of argue a weak linear relationship between the two. So for example, if the word embedding matrix satisfies some random Gaussian-like properties. So if you think of the word embeddings as independent random vectors, then you can show that there's an exact linear relationship between fs and phi of fs. And like some of the Gaussianity is satisfied in practice, but the linear relationship still does not hold exactly. And that kind of makes sense because the features fs do better. So there is something extra that it has, and it's not clear yet why. And I think that's not just by accident. I think there's probably some deficiency in the formulation that leads to this gap. So we can also use these insights to design a new objective that is an alternative to cross-entropy. I mean, of course, we don't get state-of-the-art results or anything, but this is to demonstrate that you can use insights from theory to like design new objectives. And for this new objective, so the main idea for this objective was that this theory tells us that you want to learn phi times speech star. And this objective is a more direct way to learn phi times speech star, rather than going through this softmax and taking the cross-entropy objective. It's like a L2 kind of loss that learns this phi times speech star more directly. And the nice thing about this objective is that you can not only say what the optimal represent feature map is, but you can also give a closed form expression for what the optimal word embeddings are. And that turns out to be some kind of d-dimensional, like the top D SVD of a matrix that captures the synonym structure. So in some sense, this objective can provably learn word embeddings that kind of satisfy this property that synonyms will be assigned similar embeddings. We found that, yeah, and we found that interesting. And yeah, so in the bounds that I showed here, there were a lot of constants hidden, and some of these constants actually capture some other intuitions. Like it is better for a classification task to depend on the larger set of words, larger set of completions when you set it up as a sentence completion formulation, and that corresponds to the margin of the linear classifier, and etc. And also there's a shift in the distribution that happens in the language modeling corpus and in the downstream task, and that also can affect the performance. So you want the distributions to be similar. So these are standard intuitions, but at least there's some quantities that capture them in the bound. Okay, yeah, so there are a lot of things that can be done after this. So as I said earlier, like, why is there any fundamental reason why the features themselves do better than the conditional mean features? Furthermore, can this analysis or these ideas be extended to other kind of methods, very similar methods? So something like BERT, if you're familiar with it, where rather than just predicting the next word, you take a sentence and you mask multiple words out of it, and you try to predict all of those masked words using only the rest of the sentence. So in some sense, it seems very similar to this. And actually, you can use very similar ideas if you had only masked one of the tokens. But since there are multiple tokens masked, there's some kind of mismatch between what you do in pre-training and how you solve downstream tasks. So yeah, so there's some thing of interest there. Yeah, and whether or not these ideas can be extended to other NLP tasks. So So as you mentioned earlier, as we discussed earlier, something like predicting not just one word, but a sequence of words could be one idea. But it's interesting to see how this can be extended to other tasks. And of course, a very important point that was missing here is a role of fine tuning and that of inductive biases of models and algorithms. And I don't think we are there yet in terms of having the tools to understand these questions very well. We do have some basic understanding, and I think can perhaps do some more empirical exploration to understand what are properties that these pre-trained models with particular architectures and algorithms satisfy, and see whether those properties are desirable in some ways. And of course, there's a problem of understanding other kinds of self-supervised learning methods. There are a lot of them, as I described earlier. So it's definitely a problem of interest. And I think, yeah. So yeah, that's basically what I have. I'm happy to take any questions, and feel free to email me. There's a link to the archive version of the paper here. Yeah. Thank you for listening in, and I'm happy to take questions.
Thanks. Very, very interesting. Just as my one, do you have a slide that describes your measure of the similar words have similar embeddings? You talked about that.
Right. So let me just pull that up. I think I do have a slide. It's a very rough slide, so. Okay. Okay, so so this is actually the objective function that like we construct, where now you take these SW pairs, and you can it's something like this, and you can rewrite it as doing the following. So you can take the logits that were used basically in language models, and instead of taking the softmax and taking the cross-entropy objective, you just try to look at the indicator vector for the word, and you just minimize the L2 loss. Or actually, there's no minus here. You want to, yeah, there is no minus. The negative sign here is incorrect. So you just want to minimize this loss. You just want to make it close to the indicator vector. And on average, this indicator vector will reduce to the true distribution P star of S once you take the average over the words conditioned on NES. And then that has two properties. The first is that the F for any phi, the F star is basically phi times P star. Or at least a linear function of phi times P star. And the phi star here is the SVD. So there's a top D SVD of this matrix here. So this matrix is something that we call the substitutability matrix, because it's the outer product of the P star vector. So it's a V cross V matrix. And the entry for, so if you look at the entry for any word W and a word W prime, this is measuring the correlation between the probabilities that are assigned to them across the different sentences in the corpus. So in some sense, if you have two words that always have the same probabilities assigned to them for all contexts, they are free to be substituted with each other because they're essentially have the same probabilities. And like in the sense of the distributional semantics and the distributional hypothesis proposed by Firth and Harris, this captures this idea of words that are likely to occur in the same context are basically synonyms.
Yeah. Can you actually estimate that matrix reasonably? I mean, obviously, you might worry about averages over the corpus, but you say if you just do this, you just run over the corpus a few times, you get a good estimate.
Right. So at least what we've shown here is that if you had infinite data and you could absolutely minimize this objective, you would automatically learn this matrix. So yeah, so you don't actually have this matrix in practice, right? You don't actually, you might not actually for any given context, you might not see two distinct words even in the corpus. You might just see one word and you might never see that context again.
I mean,
so you can
think about the statistics of estimating this matrix. Is this, or even as top singular vectors, is that a doable thing?
Yeah, so I don't even know how one would construct this matrix, because as I was saying, like for any given
The
context,
top,
you might.
the top singular vector is something, at least it's not a huge amount of data.
Right. But this matrix itself, this expectation
No,
of
no,
which you're going
it
to take the
certainly can't represent the
Oh,
matrix.
right. I see what you're saying. Yeah. So I mean, yeah, this is basically what it is saying, that if you can actually minimize this objective, you don't need to construct the matrix and take an SVD or something. It will implicitly, the optimal solution will learn the SVD.
Okay,
So this is one way to estimate the SVD.
So you do have a in practice definition, and my question is it a good estimate of that actual matrix?
Yes, yeah, that I'm not sure of. Like, I mean, we don't really have a good mathematical answer for how many samples you need to be able to estimate this, etc.
Okay.
I mean, and there are other issues like that. This fs, it depends on how expressive this function f is, whether or not it can express arbitrary, whether or not it can express this function. So for any phi, if you can express the phi times p star, then you are guaranteed to learn the SVD, or at least in the optimality. But even that's not clear because you might not have an expressive enough function. So yeah, in some sense, I don't have a great answer to this because it's not clear. Is the shortest answer, I think.
More questions?
A quick question. I missed, how do you define tau as the naturalness of the task?
Okay, I can go back. So tau is essentially, sorry, my laptop is being slow. Oh, wow. Okay. Okay, so I can say it in words and then we can go to the equation. So to measure tau, essentially, if you had access to the true distribution P star, you can use them as features for any given downstream task. And they can try to learn the best linear classifier on top of these features and measure the logistic regression loss that this suffers.
Okay.
So here it is. Yeah, so you use P star as the features, hypothetically, and learn the best linear classifier, and you measure the logistic regression loss. And in some sense, this is just a measure of how well do the true distributions P star, how well can they solve this task linearly.
Thank you.
I guess there's this intuition, especially for the transformers, that since the embeddings are contextual, they're not just telling you about word probabilities, but they're telling you about the syntax of the sentence, the part of speech, where it's right. So does this framework allow us to get at that? I mean, you start by talking about PFS, but of course, in the end, you can talk about the embedding.
Right. So yeah, as alluded to earlier, in some sense, this does not really answer that because all this is saying is that if you just treat the language model as a black box, which is you completely ignore what architecture was used and what it did. If you just knew that you did well on next word prediction, in some sense, you only know the input-output functionality of this black box.
You could, for example, do like the word cat is what part of speech is the word cat?
Right.
I mean, have people tried that kind of task?
Yes, I think there are a lot of recent. I'm not familiar with all of them, but there are a lot of recent work that have tried to use language models in in some innovative ways, like trying to probe it using some kind of prompts. The way we added prompts, and also the original OpenAI paper with the large language model could solve tasks using in zero shot ways by basically giving it a task description in English in some sense, and then just having it produce outputs, meaningful outputs for that input. So yeah, people have tried a bunch of these. I'm sure there are a lot of papers that do this already, and I'm not familiar with all of them, but certainly this is something that people have tried.
If I could ask one question.
Sure.
So in the language case, I guess it is kind of intuitive how you would rephrase the downstream task as like something that is related to initial task, the task A.
Mhm.
But in a lot of cases like images, for example, image GPT, when you are also doing autoregressive modeling, it's not clear if you could represent your classification task as like P star V transpose. So do you think there's something fundamentally different happening in these other modalities where we can still get good representations, or is there some link? I know this is kind of a very rough high level question, but I just wanted to get your opinion on it.
Right. So these, yeah, this is a good question. So these are actually questions that, like, at least I am thinking about, because like clearly, I mean, this is a framework, but clearly we can see that there are deficiencies with this, right? Because perhaps this is not the most efficient way to extract information out of a sentence, even, which is to phrase it as a sentence completion problem. And I think there is a lot being encoded. So as Mike also mentioned, like there's a lot of information encoded in the intermediate layers, in the output layers about like syntax, semantics, etc., that are also used somehow. But at a rough level, at least, maybe I can say this, that yeah, so in some sense, it's not just the output, let's say, it's not even just the last layer that's the last word or the representation of the last word that's useful, right? You can potentially use many things in middle. And I think all of them capture some essence of what the sentence is about.
Exactly. Yeah.
And like, it's not clear how to formalize what this essence is, but it's at least has some signal about what the sentence is talking about with respect to like the classes that you would want to separate them. Similarly with images, like if you treat like different patches as these different components, each patch has some signal about the input, even though it might be a very weak signal. And somehow maybe there's some kind of denoising happening when you do this process. So yeah, I mean, of course, there's no intuitive way to rephrase images as these, because these patches don't really mean anything.
Yeah.
And they're not discrete objects, but there is certainly some signal in there that I think can be exploited somehow by taking averages. And it's not entirely clear how, but yeah, it's possible. I mean, I maybe I can point out that we had some recent work on trying to understand reconstruction-based self-supervised learning methods, where essentially you can try to recover a missing patch of an image from the rest of the image. And if you have some underlying structures like conditional independence between the different patches, let's say, conditioned on the labels that you are interested in a task, or like even maybe fine-grained labels than those, then in some sense you can see why in order to be able to predict the missing patch, you first need to go through predicting the latent variables and then predict the patch, and then those latent variables are somehow going to be useful for the downstream task.
Yeah, I guess what I was trying to get at is like there's like what you said, that there's a lot of intermediate layers that are also encoding interesting information, and somehow they're not going to be optimal in a sense that we can reason about or like write as being related to the downstream task. So I was like curious if you think that the framework in which we should think about it has to be something fundamentally different, or this can still buy us something.
I think this can still buy something, but definitely like the more important question is, what are these intermediate layers learning? But I think what these intermediate layers can learn is also somehow determined by what task you're solving. I guess I don't have a very good like concrete answer for this, but it's just an intuition that like perhaps it disentangles different aspects in some ways, useful ways. Yeah, I don't really have a good answer to this, but I do feel like there is some level of this.
Curious what you thought about it at a high level.
No, I do think there is something there, but yeah, I think it requires a lot of, at least some amount of empirical exploration to even understand what are these encoding, like what are the intermediate representations encoding compared to the task that you asked it to solve, and why is it learning that extra information if it is, and these kind of things.
All right, thank you so much.
Yeah, no problem.
More questions? Okay, if there's no more questions, let's thank Nikunj for a very interesting talk. And there's at present nothing scheduled for next week, and then we'll have Tom Hales speak on formalization of mathematics in 2 weeks on the 24th. So I look forward to seeing you there. Thanks again.
Yeah, thank you for the invitation, and thanks everyone for attending and for asking all the questions, insightful questions. Yeah, have a good day.
You too.